Okay, so in this video, we're gonna go over the inverse trig functions and mainly just kind of deriving the derivatives of them and doing some examples using the derivatives of the inverse trig functions and some integrals as well with the inverse trig functions. Again, by now, from a previous course or from the previous video lectures that were posted on Canvas, you have an idea of the basic properties of inverse trig functions. So here we're going to look at the derivatives and how to derive them, and then just using the formulas to apply them to some problems. So let's look at, so what you see in front of here is a table of the derivative for our 6 trig functions, or the derivative of the inverses. And let's start by seeing where these formulas come from. I won't go through all 6, I'll do a couple of them here. Let's see. How about the cosine, right? If y is equal to the cosine inverse of x, right? And again, we'll assume we have the, for the proper domains and range values of x's and y's. Here we'll just focus on coming up with a formula for the derivative. So again, this is true. Again, if and only if, right, cosine of y is equal to x, right? And that's just how the relationship with the inverse, or those are how the inverse is related to the cosine. All right, now from here, let me draw a little triangle here. Excuse me. Let me get a ruler out. Let's be a little more. Let me draw here. Here. Okay. Okay, so here we have triangle here, cosine of y is equal to x. So using the definition here of a cosine, right, adjacent x over hypotenuse 1, and here the Pythagorean theorem yields me to 1 minus x squared. Okay. All right. So let's take a look at, if I want to find the derivative of the inverse, like I know a place to start is, well, I know how to find the derivative of the cosine. So why don't I start with a problem that I already know how to solve, right? So I want to take the derivative of this here. Okay, so again, right, the x is the independent variable. So with respect to x, cosine y, dx, x, right? So we'll use implicit differentiation here, right? So looking at this here, we have the derivative of the cosine is negative sine of y times dy dx, right? Or y prime, because of implicit differentiation, right? Recall, y is a function of x. All right, and on the right side, we get simply y. All right, so now I'll solve for dy dx. So dy dx is equal to negative 1 over sine of y. All right. Excuse me. All right, and then looking at, now let's go back to our calculator, right? So, excuse me, our triangle. And let's get it in terms of x, right? Because dy dx, so let's have our function in terms of x. Sine of y is the opposite over the hypotenuse. So as it turns out, this is negative 1 over the square root of 1 minus x squared. All right, so now we have the derivative with respect to x of cosine inverse of x is equal to negative 1 square root of 1 minus x squared. All right, and now we could see here, going up to our table, that's where that formula, or one of the ways we arrived at that formula. Okay. All right. So now let's do one more here just to see the process. Let's do the tangent. So let's say I wanted to find y prime for tangent inverse of x. right? And again, the relationship between the inverse, tangent, and tangent is that tangent of y is equal to x. Okay. All right. So here we have, again, let's set up our triangle, right, with angle y. And tangent is opposite over adjacent, which means here we have x squared plus 1. All right. Okay, so using the Pythagorean theorem, we get the square root of x squared plus 1. Okay, and now again, right, I don't know the derivative of the inverse tangent, but I can definitely, I've done something like finding the derivative of the tangent before. So take the derivative of both sides with respect to x. Now, excuse me, not inverse, just tangent y. And again, recall we're using secant squared y, implicit differentiation, so times dy dx. And then here we get, all right. Okay. So solving for dy dx, we get 1 over secant squared y, or simply cosine squared y, right? So the reciprocal relationship between the secant and the cosine. And looking at our triangle, we see that dy dx is equivalent to 1 over, right, adjacent over hypotenuse squared, x squared plus 1. So now we have d dx of tangent inverse is equal to 1 over x squared plus 1. All right. And then you can see where these formulas are derived, or how these formulas are derived. Okay, so now that we've seen, or at least we looked at 2 of the derivations, let's actually use these formulas to do some examples here. Okay, so let's say that all right, so let's take a look at the derivative with respect to x of sine inverse of x squared. All right. Okay, so here we're going to use the derivative of the inverse sine along with the chain rule. All right, so here we have the derivative, again, the outer function is sine. So we have derivative square root of 1 minus, and again, the argument, x squared, and square that. Okay, and then from there we multiply, right, chain rule. Now the inner function is x squared, so we multiply by 2x. All right, so we get the derivative here to be 2x, the square root of 1 minus x to the 4th. Okay, so that's how you would use that when the derivative of an inverse along with the along with the chain rule. All right, let's try another one here. How about, let's see here. How about we do another one involving the chain rule, where we have cosine sine inverse of 2w. so W is our independent variable. All right, so again, here we're going to use the chain rule a couple of times here, right? Start with the outer function. So the outer function is cosine, so the derivative of cosine is negative sine. And again, you leave everything inside there as is. We take it one function at a time, and then we add the next link in the chain, right? Working inside there. Let me switch colors here. So times. Right now I'm working in the inner function, the inverse sign. So the derivative of that is 1 over the square root of 1 minus 2w squared. Okay. All right, and then I'll multiply into that the next chain, right? That one would be the derivative of 2w, right? And that would be simply 2. All right. Okay, so let's put everything together here. Now, one thing to notice here is, for at least here, sine of sine inverse, right? Since they're inverses, the way they act, they'll simplify to 2w. And there's a 2 out here. So we get negative 4w all over the square root of 1 minus 4w squared. All right. And that would be the derivative of cosine of the sine inverse of 2w with respect to w. All right. Okay, let's see. How about we get another example going here. How about, okay. Let's see. We wanted to do the derivative with respect to x of tangent inverse, say x e to the negative 3x. Okay. Oh, okay. All right. So again, this one, it requires our use here to do the inverse tangent. So that's the outer function. So let's start with that one. 1. We get 1 plus that whole quantity squared. All right. Okay, and then from here, we can say, all right, so now once I have that, this multiply, right, chain rule. So we add the next link in the chain there and take the derivative of x times e to the negative 3x. So that would mean using the product rule, derivative of x is 1, leave the other function alone. All right, and then from here we say, all right, so leave x alone. Derivative of the exponential is e to the negative 3x. And again, don't forget the chain rule inside there. Derivative of negative 3x is negative 3. All right. And now we have, let me clean this up a little bit here. E to the negative 3x minus 3x e to the negative 3x all over 1 plus, one thing I forgot up here, squared. All right, and then x squared, multiply the exponents here, e to the negative 6x. All right, and that would be our final answer there. All right, so those are some of examples using the derivative of some inverse trig functions. Now, using the relationship between the derivative and the integral, the antiderivative, we now have 3 new indefinite integrals that we can use here, right? So, in terms of indefinite integrals, right, I can now solve any integral of this type. All right, so any integral that looks like this, where we have 1 over the square root of a squared minus x squared. right? That would be some kind of sine inverse function. So it'll be sine inverse x over a plus c. Right? And then any integral that's of the form dx over a squared plus x squared, that would be 1 over a tangent inverse of x over a plus c. Excuse me. Okay, and then our third one that we can use now is the integral of dx over x square root of x squared minus a squared, and that would be 1 over a secant inverse absolute value of x over a plus c. All right, so those are 3 antiderivatives that are a result from the definition or from our derivation of our inverse trig functions. Okay, so let's take a look at an example here. Okay, so let's say here we want to take the integral here, let's say square root of 25 minus 9x squared. Okay. All right, so one thing to notice here that it's not quite of this form right here. So one thing we can do is we could say, all right, what if I simplified this? Let's say I wanted to make it look so the coefficient is 1 in front of the x squared. And the way I do that is by factoring out a 9. And to do that, that means that that's what my inside would look like. 25 over 9 minus x squared. All right, notice when you distribute that 9, you get back the same function that you see on the left of the integral there. Okay, so now let me, I can simplify this further, right? Product of roots, I can break up into, take the individual root. So I can rewrite this as 1/3 square root, the square root of 9 is 3, that's where the 1/3 comes from, dx over 25 over 9 square root minus x squared. Okay, now looking up here, I can apply my formula that says, okay, so that means that the result of this is bring along the 1/3, right? Don't forget that, that's always, you just bring that along with the integral. Sine inverse of x over a, remember that's a squared, so a is going to be 5/3 plus c. And now, I don't like complex fractions, so let me reduce, simplify that to 3x over 5 plus c. Okay, so that will be an example where you apply those our new indefinite integral. So something that doesn't look exactly like it, but just manipulating it allows us to use that that formula. All right, thank you.